Let's talk now about transformers. These are an architecture of sequence-to-sequence models that are based solely on attention. So let's look at roughly how this works. So we've got our inputs, x1 to xn, and these all come through an embedding. After the embedding, then we've got a sequence of attention blocks. So let's call this the encoder attention block. And then we've got a sequence of those. And we get a final encoder attention block. So let's look at what a encoder attention block looks like. So what we've got an encoder attention block, so this is this. So we have input coming in, and we have some output coming out. And what we've got is a multi-headed attention block here. These are all coming into here. And this is done in parallel. So we've got all our inputs coming in through an embedding, then they're all getting a multi-head attention. So that's allowing each of the inputs to attend to any of the other inputs. So the idea is we're basically trying to get, if this is an example of translating from English to Spanish, we're trying to, in the encoder, try and get a really good understanding of this English sentence. So we do our multi-head attention, and then we are going to feed that into a plus, because what we do is we have a skip connection here. So this is exactly like a residual connection, where the multi-head attention is actually calculating the residual, or the leftover from the input. So it's how is the input changing. So this is coming up with the input plus the multi-head attention. Right? So we take this through a small neural network. By small, I mean like 2 levels deep. This is where we've got our nonlinearities. Our nonlinearities, because the multi-head attention, we don't have any nonlinearities, right? We're just going ahead and calculating k, q, and v, and doing a matrix multiply of q times k transpose, doing a softmax, multiplying it by v. None of that has any nonlinearity. So the nonlinearity comes in from our small neural network. And we do another skip connection around the small neural network, so that we can basically skip around the multi-head attention or skip around the small neural network here. And that is our output. There's some normalization that happens in here. I'm going to just kind of ignore that. So this is an encoder attention block, and we have about 6 of those, let's say. Okay, so we do a multi-head attention, followed by a small neural network. We do it again, and then we're building up a richer representation. We do it again and again and again, and at the end, we've got this abstraction that is coming out of our encoder attention block, which is very strong. Remember, for our multi-head attention, after the multi-head attention, we got these multiple heads and they just get concatenated together. So we've got, let's say, k heads, and the output of each is d, and so we've got kd coming out of here. All right. One thing to note is when we are using attention to, for instance, look at a sentence. So let's say we've got an English sentence like John bit the dog and the dog bit John. When we're doing attention, let's say we're looking at the word bit, okay, and we may be wanting to attend to who's doing the biting or who was bitten. Okay? Well, when we're doing attention, keep in mind that we are just creating a query from this word, right? And then we're trying to find matching keys. And then we are going ahead and weighting those together. Well, if we've got the same words in these sentences, then there's no difference in any of the attention. So the attention for each of these words is going to be identical in sentence number 1 as it is in sentence number 2, because of the fact that the attention is going to be these weighted values based on how well the query matches the key. But there's nothing that says where it is at all. So where it is in the sentence. So it's a bag of words approach. It's really what's happening with attention. So let's say kind of by default, attention is bag of words. And that's a problem, of course, because the order of things really does matter. John bit the dog and the dog bit John, quite different, right? The dog bit John, we're not going to get any newspaper headlines. John bit the dog, yeah, we'll get a newspaper headline from that. So we actually need somehow to encode the information, the relative information, or the position of each input. And so we do that by adding some positional encoding. So we're going to actually add in here positional encoding for each x of I. Okay? We know after we go through this embedding, we're, let's say, d big for d, we have a vector d wide for every x. And so we just need to come up with a vector d wide for every position. Now that can be done as simply as just having, let's say, John, so let's say actually the first word, we could represent with a 1 followed by all zeros. The second word we could represent with a 0 and then a 1 followed by all zeros. So basically we're just one hot encoding the word index, the location within the sentence. So 1000, 01000, 00100, 0001000, and so on. 1000, 0100, and so on. And so we can add this positional encoding. So basically what happens is what's coming to the attention block is our embedded words, plus every word has in it some information about where it is in the sentence. And so now the attention can actually attend to this information. So it can know that in that first position, a higher bit in this first position means it's at the beginning of the sentence, and so on. So it can extract this information if it finds it useful. Okay. This positional encoding is fairly straightforward. One problem with it is we can only represent d positions. And it may be that our maximum number of inputs is larger. So maybe we might allow 1,000 or 2,000 inputs here, and our d is smaller. So the way that the transformer, the original transformer architecture, did the positional encoding was actually fairly different. They actually used sine waves, so that the first position, so the position encoding is this vector that's d long. And what we can say is if we have a position, the entry in the ith location of the vector is going to be sine of the position divided by some function of I, where this function doesn't particularly matter. But just note that we have different values here. So we have different sine functions for every entry here, and that allows us to, by taking some linear combination of these, really get us to any position we want. That was the theory. It turns out that this funky position encoding and this simpler encoding both work just as well. The difference is we can represent longer positions, because here we're limited to just d using the 1 hot. So once we've done the positional encoding, really, now we no longer have this bag of words problem, because each word coming in has some information about where it is. That then gets fed into the attention. If the attention is interested in it, it has the information. It all gets sort of learned. And what comes out at the top really is then our encoded let's just look at encoded sentence, assuming we were doing a sentence here. How is this different, though, from an RNN, right? An RNN goes through some work and eventually comes out with an encoded sentence. Well, what's different is a couple things. First, in the RNN, again, we can't attend to the entire sentence. So we can, in a forward RNN, only attend to what we've seen so far, and in a backward RNN, only attend to what has happened afterward. Here, we get to look at the entirety of the sentence, and through our different attention blocks, we're building up this higher and higher abstraction, just as we'd have a multi-layer RNN that's doing this. Once we've got this encoded sentence coming out, then this looks sort of like feeding in the output of an encoder RNN into a decoder RNN, except here we're feeding in the output of an encoder attention of the input to a decoder. Okay? The decoder is not going to be an RNN either. The decoder is also going to be using attention blocks. So let's look at how that looks. Like an RNN, we're going to have to feed in information. So for example, if our problem is something like the cat in the hat is our X, and our Y is el gato en el sombrero, as we're doing this training, we're going to need to feed in prompts and get out the associated Y hats. So we're going to feed in here our outputs, but these are all going to be shifted right. Okay? So this is just like when we're training sequence-to-sequence RNN for translation. We will, for the decoder RNN, we will, at the first time step, get out the probabilities for Y1 hat. And then we will feed in what Y1 actually was at the next step, and then get the probabilities for Y2 hat. Feed in what Y2 actually was, get out the probabilities for Y3 hat. May not have mentioned the name of that, it's called teacher forcing. So that's as we're doing our training to ensure that it's going to learn that it should be having a higher probability for L, for Y1 hat, gato, for Y2 hat, and so on. We're doing the same thing here with our teacher forcing in that we're feeding in el gato and el sombrero offset by 1. Okay. So that when we're generating Y2 hat, it'll know the first word was L. We're going to feed this into embedding. Do we need to have positional encoding here? Yes, because the order, again, of this matters. So we're going to feed in positional encoding so that after the positional encoding, we'll not only know what each word is, but also embedded in it where it is, right? We know that the order of these does match the order here. The problem is when we're doing the query key values and we get this weighted context, we've lost all of our positions. So by ensuring that it's not just the order in which these occur, but actually the actual value itself contains the position, that'll allow us to ensure that our weighted sum can actually include position information. We're going to feed this into a decoder attention block. And we have a series of these. Again, the number's about 6, I think. 6 encoder attention blocks, 6 decoder attention blocks for the original transformer paper. And our output of this then is going to be a linear layer. And we'll feed this through a softmax. And these are our output probabilities. Okay, so there are a couple things to note here. So one thing to note is currently we don't have any connection between the encoded sentence and the output sentence. So we will deal with that in a moment when we look at what a decoder attention block is. So the output of the encoder, the topmost encoder attention block, is actually going to be fed in as input to each of the decoder attention blocks so that the decoder can attend to the entirety of the encoding here. Because remember, our encoded sentence is not just really a sentence, it's actually encoded positions for every, so we have a encoding for the, encoding for cat, encoding for in, encoding for the, and encoding for hat. And really maybe we just think of it as the first, the second, the third, the fourth, and the fifth. We have encodings, and we've built these up from multiple levels of attention. So there's been first a level of attention that just attends to these words, and then we built up a higher representation, and then there's that level of attention that attends to that higher representation, we get an even higher representation, and so on. So we've got this fairly high representation here of all this, and that's going to be fed into these decoder attention blocks. Unlike the RNN, we're not doling these out one by one. This is all done in parallel. Okay, so we're going to actually be feeding in all these x1s to xn's, coming up with this attention block, feeding in the y1s to yt's, shifted by 1, all through these attention blocks, and then come up with a linear layer and do our output. So again, it's not one by one by one, it's all in parallel. let's look at the decoder attention block in more detail. So the decoder attention block, we have input coming in. And this comes in and actually goes through masked multi-head attention. So it's like multi-head attention, but it's masked in some way. And here's why we get this masking. We would like, when we're outputting, let's say the 10th word here, to be able to attend to all 9 of the previous words of the output. Okay? So when we're trying to calculate y10 hat, we'd like to be able to attend to all of y1 through y9. It'd be cheating, though, to be looking at y10 itself, right? Because we have the actual input here, the actual correct value for y10, and we certainly don't want to attend to that. And we don't want to attend to any later values as well, okay? Because when we're doing generation, we don't have access to that. So we need to do some form of attention where we can ignore a swath of the keys. And that's what the masked multi-head attention is. So the masking is going to be done differently based on where the query is. So if the query is for this first position here where we're trying to, that corresponds to trying to output y1 hat, then we're going to mask everything. Okay? If we are, on the other hand, trying to output yt hat, then we are going to be not masking anything. So we construct this mask that basically just says, hey, when you are doing this multiplication of q by k, go ahead and take the result and mask out some of them. And by masking, we just mean, so if we look at it, right, we've got our softmax of q k transpose. So if we just go ahead and do a multiplication by an appropriate matrix, right, with the right number of zeros and the right number of ones, we can just set a bunch of these, actually. So we got the softmax of qkt. We don't want to take the output of this and mask it, because all of a sudden then we're going to get probabilities that don't add up to 1. Right? So if we just take some of the probabilities for anything beyond here and that are later that should be masked and set them to 0, then all of a sudden the previous probabilities won't add up to 1. So instead we're going to take the qkt and just multiply by an appropriate matrix such that we set the things that should be masked to very negative values, right? Because when we take the softmax, those will effectively become 0. So we here mask all this in parallel. So we set masked values to effectively negative infinity, right? Very small numbers for our qkt. Then when we do the softmax, all those are going to be set to probabilities of 0, which means when we do our weighted sum, they're going to be ignored. So what this allows us to do is not have to go through one by one, but instead just by using different masks for the first word, the second word, the third word, and so on, we can ignore everything that's later. So that's what we're doing with our masked multi-head attention. Okay, as always, we're going to have a skip connection, and then we're going to have a multi-head attention. Right? So this one's not masked. I'm going to show this, right? So this is the blown up version of one of these. I'm going to show this output coming in here, okay? Because it's coming into each of the decoder attention blocks. And when it's coming, it's not coming into the masked multi-head attention subblock. It's coming into the multi-head attention subblock. So what happens is the output of the masked multi-head attention becomes our Q, right? So we've got our queries that are coming out of here. So that's going to be our queries. So our queries are going to be based on, in the first attention block, just the unmasked input. So it'll be based on the input we've seen so far. In future attention blocks. It's going to be based on all the information we have about that location. So we feed in our queries here, and our keys are from here. So what does that mean? That means that the multi-head attention, what's this attending to? This is attending to the previous output, okay? Which makes sense that as we are generating a translated sentence, that we care about the words that have been output so far, right? And then this guy is attending to the entire input. So we get to attend to both the output and also the entire input. The attending to the output is actually nice. So in an RNN, as we were doing output, even when we were using attention, we were just attending to various parts of the input. Now we can attend also to what we've output so far. All right, and what do we do after this? Of course, we're also going to do a skip connection. And then we're going to have a feed forward. Then we're going to have a small neural network. Again, 2 layers, let's say, which will be residual. And after that small neural network, that'll be output. So each of the decoder attention blocks has this form. We go through, we attend to the output so far at whatever level of abstraction we've got. So at the beginning, it's a fairly low level abstraction. As we go higher and higher, it becomes higher and higher abstractions that we are attending to. It's masked, so we're not attending, we're attending to the right stuff, which is basically everything before us, but nothing at our location or afterwards. And this masking, of course, the mask is different for every location here. And now we've attended to the output, we go ahead and attend to the input, okay? Where again, our queries, and this is all multi-head as well, our queries are what's coming out of the previous multi-head attention, and our keys then are the entire input, so the fully abstract version of the entire input. We feed that into a small neural network, that's where we get our nonlinearities, and we go out. We do this several times, and then a final linear layer, a softmax, and that gives us our output probabilities. So advantages of this are in terms of speed of training, for example, because all of our input and our output is being done in parallel. Okay? We don't have this bottleneck of going through one by one for every input like we do in an RNN, or one by one for every output like we do on an RNN. It's just some giant matrix multiplications that we're doing. So that speed really means that we can afford to have larger models because we know how to train them in a reasonable amount of time. That's really transformers. Transformers have really made a huge difference in the last 4 years. So different kinds of transformers, for instance, include, so we have, for instance, BERT, GPT-2, GPT-3, GPT-3 having hundreds of billions of parameters, trained on a huge amount of data, basically sort of everything on the internet can be fine. So GPT-3 has, this is not available for general use, so the weights are not available. Instead, there's an API that's available from Microsoft, which has licensed it. So you can actually use a license, and you can do amazing things with GPT-3. So it's been trained so well that you can, for instance, do what it's called one-shot learning. So you can, for instance, give it an example and tell it what you want. So for instance, you might provide to GPT-3 the prompt question, let's say, what's the capital of California? And then your answer could be, let's say, Sacramento. This is the prompt you're going to feed into GPT-3. GPT-3 has not been trained as a question answering device, but instead you'll feed in an example kind of what you're looking for, and then what's your real question? Your question is going to be, what's the height of Kilimanjaro? And then A. Well, if this is your prompt, if you're asking a human, well, here's some text, Q, what is the capital of California? A, Sacramento. Q, what is the height of Kilimanjaro? A, colon. Clearly the next thing to produce would be the answer to this question. GPT-3 can do things like that. GPT-3 can create poetry. GPT-3 can write blog posts. You give it kind of a prelude of what you want, and it will produce that for you. GPT-3 can create LaTeX from a description of your equation. Okay. How does it do that? Well, it's not trained on doing that. Instead, you would have to provide some sort of a prompt. The prompt is going to have to be enough to tell GPT-3 kind of what it's supposed to be doing. So you might say, for instance, a description, and then we have a description of, a squared plus bx plus c over 3p. And then the answer, or let's say the description is that, let's say the LaTeX is frac a squared plus bx plus c 3p. And then you could say description again. So this could be your sort of generic LaTeX prompt. And then if you want to translate a particular description into LaTeX, you would feed this, followed by your description, followed by the word LaTeX. So if you had a particular description you were looking for, like let's say you're looking for y hat sub 3, and then you put in your LaTeX prompt. So it could then feed this into GPT-3, and what you expect from this prompt would be something like. So there's been some suggestion that in the future, maybe what we're going to be doing for machine learning is not really coming up with the data sets, but instead just figuring out the right prompts to be using for these multi-purpose trained machines. And the fact is, it's just so big and trained on so much data that it has lots and lots of information in it. So transformers, there has been some work on using them in non-text problems, but for now, certainly in natural language processing, transformer models are king.